A planet can sit in the perfect zone for life and still be dead. That is the part the headline usually leaves out. Somewhere beyond the solar system, a star dims by a fraction so small the human eye could never notice it. A telescope catches the dip, a computer model measures the rhythm. Astronomers pull a planet out of the darkness, not by seeing oceans, not by seeing clouds, not by seeing a blue world hanging in space, but by watching light disappear for a few hours. Then the words arrive: Earth-like, potentially habitable. In the habitable zone, the phrase moves faster than the science behind it. It jumps from papers to headlines, from headlines to thumbnails, from thumbnails into the human imagination. Within minutes, a world that was only a shadow in starlight becomes a place. People picture a red sun rising over black water. They picture clouds curling over alien continents. They picture another Earth waiting quietly in another system, not close enough to reach, but close enough to hope. The planet may be real, the hope may be honest. The picture is usually fiction. The habitable zone does not mean a planet is habitable. It does not mean there are oceans. It does not mean there is air. It does not mean the surface is safe. It does not mean life has a chance. It only means the planet receives the kind of stellar energy that could allow liquid water on the surface if the planet has the right atmosphere, the right pressure, the right history, the right climate, the right chemistry, and enough stability to keep everything from collapsing into ice, steam, radiation, or rock. That word "if" is where the myth dies. The public version of the habitable zone is simple. Not too hot, not too cold, just right. A green ring around a star. Put a planet inside that ring and the mind begins building biology. The scientific version is coldal. It is a screening tool, a way to decide which worlds deserve closer attention. It says a planet is in the right neighborhood for one condition life seems to need. It does not say the house has walls, a roof, air, water, or anyone inside. A world can be in the zone and still be stripped bare. It can be in the zone and still be locked in permanent daylight on one side and permanent night on the other. It can be in the zone and still be blasted by a star that looks small and harmless until it erupts. It can be in the zone and still have no magnetic protection worth talking about. It can be in the zone and still lose its atmosphere grain by grain, molecule by molecule, over deep time. It can be in the zone and still become Venus. It can be in the zone and still become Mars. That is the sentence hiding under the excitement. The universe can put a planet exactly where we want it and still refuse to make it alive. The misunderstanding starts because the search for life has always been haunted by Earth. We only know one living planet, one example, one blue exception. Every definition we build has Earth's fingerprints on it. We look for water because Earth life uses water. We look for rocky surfaces because Earth life began on a rocky planet. We look for atmosphere because Earth's atmosphere protects, warms, and reveals life. We look for sunlight because Earth's biosphere feeds on it. None of this is. It is the only honest place to begin, but a beginning can become a trap when people forget it is a beginning. Earth is not alive because it sits in a comfortable orbit. Earth is alive because a brutal chain of conditions held together for billions of years. It had to keep its water. It had to keep enough air. It had to avoid the runaway greenhouse fate of Venus. It had to avoid becoming a third end like Mars.
Yeah.
Geology, chemistry, pressure, circulation, feedback, time, and luck. It needed catastrophe not to happen too early, too often, or too completely. The habitable zone captures one piece of that story. It leaves out almost everything that made the story survive. Look at Venus. If you only knew its size, you might be tempted. It is close to Earth in mass, close to Earth in radius. A rocky planet next door. Venus was imagined with jungles, swamps, oceans, clouds hiding a wet world underneath. The clouds were real. The dream was not. Venus is not Earth's warm sister. It is a warning. Its atmosphere is thick with carbon dioxide. Its pressure at the surface is crushing. Its clouds are laced with sulfuric acid. Its surface is hot enough to destroy machines quickly and melt metals we associate with industrial furnaces. It shows what happens when a planet's atmosphere does not merely support climate, but traps it in a deadly state. The distance from the sun mattered. The atmosphere decided the sentence. Mars tells the other side of the story. Is not a furnace. It is a world that seems to have lost too much. The valleys, minerals, delta, and lakebed-like structures scattered across its surface point toward an ancient Mars where liquid water once flowed. That world is gone. The Mars we see now has a thin atmosphere, low pressure, bitter cold, exposed radiation, dust, ice, and silence. It did not simply sit in the wrong place. It failed to keep the environmental machinery that surface water needs. Venus and Mars sit beside Earth like two dead explanations. Too much atmosphere, too little atmosphere, too much heat trapped, too much air lost. The habitable zone alone cannot tell the difference until it is too late. A planet is not just a dot at the right distance. It is a history moving around a star. That is where the Earth-like planet headline becomes dangerous. It compresses a long list of unknowns into one emotional shortcut. Sometimes Earth-like means close to Earth's size, sometimes it means rocky, sometimes it means receiving similar energy from its star, sometimes it means only that the planet is not a gas giant and not obviously frozen or scorched by orbital distance alone. In the public imagination, those careful meanings collapse into one picture: blue, cloudy, alive. But an Earth-sized planet can be airless. A rocky planet can be sterile. A temperate planet poisonous skies. A planet with water vapor can have no ocean. A planet with methane can still have no biology. A planet with carbon dioxide can be Mars, Venus, Earth, or something stranger than all three. Earth-like is not a world, it is often a measurement wearing a dream. The telescope does not see what the hearts paint. Most exoplanets are not images, they are deductions. A star dims. A star wobbles. A spectrum shifts. A model fits the data better than another model. The planet emerges from mathematics, precision, repetition, and uncertainty. That is not a weakness, it is astonishing. We are detecting worlds so far away that their light is swallowed by the stars they orbit. We are measuring planets that would vanish beside a speck of dust if placed against the brightness of their suns. We are reading atmospheres from tiny changes in starlight, searching for molecules and signals so delicate that stellar spots, clouds, hazes, and instrument noise can change the interpretation. The science is powerful. The certainty is limited. That distinction matters. When a paper says a planet may be in the habitable zone, it often means the planet receives a level of radiation that makes surface liquid water plausible under suitable atmospheric conditions. It does not say those suitable conditions exist. It does not say the atmosphere is known. It does not say water has been found. It does not say life is likely. It may not even say the surface is accessible, especially if the planet is a sub-Neptune wrapped in a thick envelope rather than a rocky world like Earth. The headline trims the caution, the imagination supplies the ocean. This is how a scientific filter becomes a public myth. The myth gets stronger because the habitable zone sounds like a place, a region, a safe band in space. The old nickname makes it even stronger. The Goldilocks zone. Not too hot, not too cold, just right. It is memorable because it is simple. It is misleading for the same reason. The universe is not a children's story. A planet can sit where the average energy seems right and still fail through every deeper test. The atmosphere may not exist. That alone can kill the dream. Without enough pressure, liquid water cannot remain stable across the surface the way it does on Earth. Without air, there is little shielding from radiation, little heat redistribution, little weather, little climate. The planet becomes rock directly exposed to space, heated and cooled without the softening layer that makes Earth's surface livable. Or the atmosphere may be too thick. That sounds less frightening until Venus appears. Air is not automatically good. A planet can drown in its own greenhouse. A thick atmosphere can crush the surface, trap heat, hide it under opaque clouds, and turn the world into a pressure cooker. The surface may exist, but not as a place life as we know it could endure. Or the atmosphere may be the wrong kind. Hydrogen-rich envelopes can make a planet more like a mini Neptune than an Earth. Carbon dioxide can warm a cold planet or push a warm planet toward disaster. Methane can shape climate and chemistry without proving biology. Oxygen can be produced by life, but certain non-biological processes may also generate oxygen under special conditions, especially on worlds losing water. Every gas means something only inside a context. The habitable zone does not give you the context. It only points to the suspect. A planet can have the right orbit and the wrong sky. This is why the real question is not whether a planet is in the habitable zone. The real question is what kind of planet the zone has produced. The star matters. The atmosphere matters. Smatters, the interior matters. Rotation matters. Water inventory matters. Geological cycling matters. Impacts matter. The age of the system matters. The violence of the star's youth matters. The chemistry of the atmosphere matters. The history of escape matters. The presence of clouds matters. The relationship between light and air matters. Habitability is not a location, it is a negotiation. A living world has to keep negotiating with its star, its atmosphere, its oceans, its rocks, and its own past. It has to lose slowly enough replenish fast enough, regulate gently enough, and remain stable long enough for chemistry to become biology. There is no green ring that performs that work for it. Red dwarf stars make this painfully clear. They are everywhere, small, cool, dim, long-lived. The galaxy is full of them. Because they are faint, their habitable zones lie close in. A planet can receive Earth-like energy while orbiting far closer to its star than Earth orbits the Sun. That closeness makes these planets easier to detect. They pass in front of their stars more often. They block a larger fraction of the star's light than an Earth-sized planet would block around a Sun-sized star. Their signals repeat quickly. For astronomers, they are irresistible. For planets, that closeness may be dangerous. Near a small star, tidal forces become strong. Over time, they can slow a planet's rotation until one side always faces the star. A tidally locked planet does not have days and nights like Earth. It has a permanent day side and a permanent night side. One hemisphere stares into the star forever. The other never sees sunrise. It is one of the most haunting images in planetary science, a world with no morning, a star frozen in the sky. A night that has lasted for geological time. The simple version says such a planet is dead. The real version is more interesting and more unsettling. Tidal locking does not automatically kill habitability. A thick enough atmosphere might carry heat from day to night. Winds could move warmth across the planet. Oceans, if they exist, could transport energy. Clouds might form above the dayside and reflect enough light to cool the surface. Some climate models allow regions of stability, especially near the terminator, the twilight boundary between eternal day and eternal night. That possibility matters, but it does not rescue the myth. It complicates it. A tidally locked world can survive only if other systems cooperate. The atmosphere must not freeze out on the night side. Heat must circulate. The day side must not overheat. The night side must not become a trap where volatile gases collapse into ice. The climate must avoid extremes that simple orbital distance cannot predict. So the question changes. Not is it in the habitable zone, but can this locked world move heat well enough to avoid destroying itself? The orbit does not answer. The star adds another threat. Many red dwarfs, especially active ones, can flare. A flare is not a gentle brightening. Radiation erupts outward. X-rays and ultraviolet light can slam into the upper atmospheres of nearby planets. Charged particles may interact with magnetic fields or exposed gases. Over time, this can alter chemistry, heat the upper atmosphere, and contribute to atmospheric loss. A planet close enough to be warm around a dim red star may also be close enough to suffer. This is the savage bargain of red dwarf habitability. The star is small, so the planet must be near. The planet is near, so the star becomes harder to survive. Again, this does not mean all red dwarf planets are dead. That would be lazy science. Some red dwarfs are quieter than others. Some planets may retain atmospheres. Some may rebuild secondary atmospheres through volcanic outgassing. Some may have enough mass, chemistry, or protection to remain interesting. Some may occupy conditions models have not fully explored. The correct answer is not despair. The correct answer is caution, but caution is exactly what the headline tends to remove. A red dwarf planet can sit in the habitable zone while its atmosphere is slowly being sandblasted by its star. The green ring stays, the air disappears. Atmospheric escape is one of the quiet killers of habitability. It does not need one dramatic explosion. It can work through time. Molecules in the upper atmosphere gain energy. Light breaks water apart, hydrogen slips away. Stellar wind interacts with exposed gases. Impacts remove air. A planet's gravity fails to hold what it needs. The atmosphere thins. Surface pressure falls. Water becomes unstable. Radiation reaches deeper. Climate collapses. A dead world may not die in a single event. It may leak. Mars is the local reminder. It did not always look as it does now. Ancient Mars seems to have had conditions that allowed liquid water at the surface. It had a different atmosphere, a different climate, a different face. That world faded. Much of the atmosphere was lost. Water became ice, vapor, mineral memory, and scattered traces. Mars shows that a planet can have a more habitable past and still end as a cold desert. Now move that lesson to a small planet around an active star. Move it closer, give it flares, give it ultraviolet radiation. Give it a long pre-main sequence phase, where the star was brighter in ways that could damage early water inventories. Suddenly the habitable zone is not a safe ring. It is the scene of a crime. The planet may be found at the right distance today, but its past may already have destroyed it. That is another part of the myth. People imagine the habitable zone as a present tense label. The planet is there now, so it might be living now, but habitability is historical. A planet must not merely enter the zone. It must preserve the ingredients through time. A world can be in a good orbit after losing its ocean. A world can receive gentle light after ultraviolet radiation has stripped its hydrogen away. A world can look temperate after a runaway greenhouse phase has left it dry. A world can sit in the right place too late. The zone does not remember, the planet does. K218b shows how this becomes even messier when a planet is not simply Earth-sized rock. It sits in the habitable zone of a cool star, and because it has been studied with powerful instruments, it has become one of the most discussed exoplanets in public science. Its atmosphere has been reported to contain molecules such as methane and carbon dioxide. There have been debated claims involving dimethyl sulfide or related molecules, which on Earth can be associated with life. The possibility sparked enormous attention because a molecule connected with biology on Earth, detected on a distant world, sounds like the opening line of a new era, but the careful version is much less cinematic. K218b is not Earth, it is a sub-Neptune, larger and more massive than our planet. Its nature is still debated. It may have a hydrogen-rich atmosphere. It may not have an accessible ocean surface. The interpretation of its spectrum is difficult. Molecules that seem exciting may be uncertain, model-dependent, or explainable without life. A possible biosignature is not a biosignature confirmed. A planet in the habitable zone is not a habitable planet confirmed. A world with intriguing atmospheric chemistry is not a world with biology. That distinction is everything. K218b became famous partly because it sits at the edge of public desire. It is close enough to the dream to attract attention and different enough from Earth to resist simple storytelling. It is a perfect case study in how a headline can outrun evidence. The disciplined sentence is not "we found life." It is not even "we found a habitable ocean." It is that the planet is scientifically fascinating, the data are difficult, several interpretations are being tested, and no claim of life is established. That sounds less viral, it is more honest, and it is far more interesting than pretending uncertainty is a failure. TRAPPIST-1 creates a different kind of tension. A small red dwarf, 7 known rocky planets, several near the region where liquid water could be possible under the right conditions. A compact system, almost like a scaled-down solar system built around a dim ember. It is hard not to be drawn in. The planets are close enough to their star to transit often. They are valuable targets. They are among the worlds people most often imagine when thinking about life around red dwarfs. But TRAPPIST-1 is not a fairy tale, it is a test. Some observations have already narrowed atmospheric possibilities for some of its planets. Certain Earth-like atmospheres have not shown up where people might have hoped. Some planets may be airless or lack the thick atmospheres needed to redistribute heat. Others remain uncertain. The system is still scientifically precious, but not because it confirms the fantasy. It is precious because it reveals how hard the fantasy is to earn. The phrase Earth-size did not make the planets Earth. The phrase habitable zone did not give them air. The phrase promising did not settle their climates. TRAPPIST-1 is a reminder that astronomy is often an act of subtraction. Scientists begin with many possibilities, then observations remove some. A thick atmosphere becomes less likely. A certain molecule is not detected. Under new constraints, the beautiful illustration remains online, but the real planet becomes narrower, stranger, and less obedient to hope. That is not disappointment, that is discovery. A planet is not less real because it refuses to be the planet we wanted. The deeper story is that the universe is full of almosts. Almost Earth-sized, almost temperate, almost wet, almost safe, almost alive. The habitable zone is the kingdom of almost. And almost is where science becomes both thrilling and brutal. The public often wants the search for life to feel like a treasure hunt. Find the right star, find the right orbit, find the right planet, and the answer appears. But the real search is closer to an investigation where every clue can be forged by nature. Water vapor can mean water but not necessarily oceans. Oxygen can mean life but not necessarily. Methane can mean biology, geology, or chemistry depending on the setting. Carbon dioxide can mean atmosphere, greenhouse warming, volcanic outgassing, or a Venus-like warning. Clouds can hide everything. Hazes can flatten spectra. Stellar activity can mimic or distort signals. There is no single clue that saves us from thinking. The universe does not label living planets in a language written for us. This is why the science of biosignatures is filled with caution. A biosignature is not just a gas. It is a gas in context. The same molecule can have different meanings on different worlds. Oxygen with methane in persistent disequilibrium on a temperate rocky planet would be exciting. But it would still demand careful testing. Abiotic pathways must be considered. The star's ultraviolet spectrum must be known. The planet's water history matters. Surface pressures matters. Atmospheric escape matters. Geological sources matter. Life is not the only process that changes atmospheres. Dead planets can be chemically dramatic. A world can produce an interesting spectrum without producing a single living cell. This is where the myth becomes most dangerous. People imagine that the habitable zone is the hard part and life detection is the easy sequel. In reality, finding the zone is the crude sorting step. The hard part is learning whether the planet has kept the delicate physical conditions that make biology possible, and whether any atmospheric signal can be interpreted without fooling ourselves. The galaxy may contain countless planets that look promising only because we cannot yet see them clearly. Distance hides failure. A planet seen from far away can appear more hopeful than it is because the data are thin. If you only know its radius and orbit, imagination has room to work. If you later learn it has no atmosphere, the room closes. If you learn the star is more active than expected, the room closes further. If you learn the planet is a Neptune instead of a rocky surface world, the room changes shape. If you learn a claimed molecule is uncertain, the room grows darker. Science does not kill wonder by adding detail. It kills the wrong wonder and replaces it with better wonder. The wrong wonder says, this planet is in the zone, so maybe it is another Earth. The better wonder asks, what kind of world survives the conditions that make another Earth possible? That question is harder. It is also more beautiful, because Earth becomes stranger when you stop treating it as normal. We live on a planet that kept surface oceans for most of its history. A planet with air pressure strong enough for liquid water, but not so crushing that the surface becomes hell. A planet with a greenhouse effect strong enough to warm, but not so strong that oceans boiled away. A planet with an active interior, recycling, weathering, volcanism, and carbon movement over deep time. A planet with a star stable enough for biology to persist. A planet that endured impacts, snowball episodes, oxygenation, extinctions, continental drift, and solar brightening without losing its living surface completely. Earth is not simply in the right place. Earth is a long-term balancing act. The habitable zone points to the stage. It does not explain the performance. A planet can fail at the inner edge. Too close to the star, water vapor can become part of runaway greenhouse. More heat evaporates more water. Water vapor traps more heat. The upper atmosphere becomes wetter. Ultraviolet light can break water apart. Hydrogen escapes. The planet dries. What began as a blue world can become a furnace. This is the nightmare beneath every beautiful ocean illustration. Water can help life. Water can also help destroy habitability if the climate tips in the wrong direction. A planet can fail at the outer edge. Too little stellar energy, and ice expands. Ice reflects light. Reflected light means less warming. The freeze deepens. Carbon dioxide may help if enough accumulates, but if weathering, volcanism, atmospheric collapse, or cloud processes do not cooperate, the world can lock into cold. It may keep water but buried. It may be wet in inventory and dead at the surface. Water present is not the same as water available. A frozen world can be rich in water and poor in habitability. A planet can fail because of rotation, spin too slowly, lock to the star, build extreme gradients, spin differently and atmospheric circulation changes. Clouds move, heat transport changes. A world that seems temperate by simple calculations may become climate chaos under realistic dynamics. A planet can fail because of mass. Too small, and it may not hold air. Too large, and it may trap a thick envelope or produce crushing pressures. Just rocky enough to interest us, not Earth-like enough to save the surface. A planet can fail because of geology. Without long-term cycle, carbon dioxide may not be regulated. Too much volcanic gas can alter the atmosphere. Too little geological activity can starve the climate of replenishment. Weathering, outgassing, continents, oceans, and crust all shape climate in ways an orbital diagram cannot show. A planet can fail because of time. This may be the cruelest one. There may be windows of habitability. A world could be wet for a few 100 million years, then lose its atmosphere. Another could freeze early and thaw later. Another could remain stable only after its star calms down, but by then its water is gone. Another could become habitable in the future when stellar brightness changes, but not now. Habitability is not always permanent. It can be a season in a planet's life. The habitable zone is usually drawn as if the planet either belongs or does not. Real worlds drift through possibility. Even the sun changes. It was dimmer in the ancient past and will brighten in the future. The habitable zone around a star moves over time. A planet that begins comfortable may later become too warm. A planet that begins frozen may later thaw. The phrase continuously habitable zone tries to capture this time dimension, but it still cannot handle all the messy details of atmospheres, geology, and planetary evolution. Life needs not just a place, it needs a durable place, or at least a place durable enough. That is one reason Earth's history matters so much. Life appeared early in Earth's history, but complex life took far longer. For billions of years, the planet's surface remained within ranges that allowed oceans and biology to persist. That endurance may be common. It may be rare. We do not know. Finding planets in habitable zones will not answer that by itself. We need to know how many keep their atmospheres, how many keep water, how many avoid runaway greenhouse states, how many maintain climate cycling, how many orbit stars that do not destroy them early, how many remain stable for timescales biology can use. Those are not details, they are the story. The public wants alien life to be a yes or no question. The science keeps returning to a more difficult question. What kind of planet are we dealing with? A planet might be a bare rock in a good orbit, a Venus in a good orbit, a Mars in a good orbit, a locked world with narrow habitable regions, a water world with no exposed land, a sub-Neptune with a hidden or unreachable ocean, a frozen shell with liquid water underneath, a chemically active but lifeless atmosphere, a world with life underground but no detectable atmospheric signal, a living planet whose biosphere looks nothing like Earth's and leaves signals we do not recognize. The habitable zone includes possibilities that range from paradise to corpse. That is why the phrase needs to be handled like a blade, not a slogan. The most responsible way to hear habitable zone is not as an answer. It is an invitation to ask harder questions. Does the planet have an atmosphere? What is it made of? How thick is it? Can it maintain surface pressure? Does it show signs of water? And what would that mean in context? Is the star active? How old is the system? Is the planet tidally locked? Could heat move around the planet? Could the atmosphere survive early stellar activity? Is there evidence for clouds or hazes? Is the planet rocky, or does its size hide a volatile envelope? Is the climate stable in models? Could observed gases be abiotic? What observations would distinguish between the possibilities? That is the real shape of the search, not a green ring. A courtroom, every planet is on trial, and almost every witness is unreliable until cross-examined. The trouble is that careful uncertainty sounds weak to audiences trained on certainty. This planet could be interesting, cannot compete easily with new Earth discovered. Possible atmospheric molecule under debate, cannot compete with sign of life found. Temperate sub-Neptune with uncertain composition, cannot compete with ocean world. But the careful sentences are where the truth lives. When scientists argue over K218b, that is not science failing. That is science refusing to let desire decide. When JWST observations narrow what atmospheres may exist around TRAPPIST-1 planet, that is not the dream dying. That is the dream being tested against reality. When models disagree about tidally locked climates, that is not confusion to be mocked. That is the frontier taking shape. The frontier is not made of answers. It is made of better questions. A useful myth gets people to look up. A dangerous myth makes them think looking up is enough. The habitable zone has done both. It has given the public a doorway into exoplanet science. It has helped people understand why distance from a star matters. It has made invisible worlds emotionally reachable. It has shaped missions, target lists, and conversations about life beyond Earth. It is one of the most successful ideas in public astronomy because it gives a simple spatial form to a profound question. But the same simplicity has made it too easy to oversell. The habitable zone became a shortcut for habitability. Habitability became a shortcut for life. Life became a shortcut for aliens. And suddenly a faint dip in starlight becomes a civilization in the imagination. The correction is not to drain the wonder from the search. The correction is to aim the wonder at the right thing. The wonder is not that we have found a list of second Earths waiting for us. We have not. The wonder is that we can now begin to separate the almost Earths from the dead almosts. That may sound harsher. It is actually more profound. A galaxy full of planets is not automatically a galaxy full of live experiments. Some fail through fire. Some fail through ice. Some fail through radiation. Some fail through loss. Some fail because the star was wrong. Some fail because the atmosphere was wrong. Some fail because timing was wrong. Some may succeed in ways we have not imagined. The habitable zone is where many of those experiments become visible to us. It is not the result, it is the lab bench. Think of a beautiful planet in an artist's illustration: blue oceans, white clouds, a calm star, a thin bright line of atmosphere glowing along the limb. It looks like home from far away. Now remove what has not been measured, roam the ocean. No telescope has seen it, roam the clouds. They may be artistic, roam the blue. The color may be chosen for emotion, roam the continents. They are imagined, roam the breathable air. It is not detected, roam the stable climate. It is modeled at best, roam the surface pressure. Unknown, roam the magnetic field. Unknown, roam the interior cycling. Unknown, roam the long-term water history. What remains? A planet. That is still magnificent. But it is not the same planet the image promised. This is not an argument against imagination. Without imagination, science would be a cold machine without a human pulse. The problem is not imagining possible worlds. The problem is forgetting where imagination begins. A good exoplanet illustration should feel like a question. Too often, it is received as evidence. The same thing happens with words. Potentially habitable should feel like a question. Too often, it is heard as a near answer. The phrase surface liquid water carries the same danger. Liquid water is essential for life as we know it, but surface liquid water is not easy to keep. It needs pressure, it needs temperature, it needs an atmosphere. It needs a planet that has not lost too much hydrogen, not trapped too much heat, not frozen under reflective ice, not buried its water too deep, not turned its ocean into steam. Even if water is present, life still has demands. It needs energy gradient, chemistry, stability, and time. It needs molecules that can build complexity. It needs environments that can preserve, concentrate, high cycle minerals, surface, vents, or impact, or other conditions depending on the origin pathway. We do not yet know exactly how life began on Earth, which means we cannot confidently say how often it begins elsewhere. The habitable zone is often treated as though it solves the origin problem. It does not. It only says one important solvent might be possible in one important state. That is a thin bridge over a very deep canyon. The origin of life is still one of the hardest questions in science. We know life emerged on Earth early enough to suggest it may not be impossibly rare under the right conditions. But we have one example. And one example is a dangerous foundation for cosmic statistics. Maybe life begins readily when planets are wet and stable. Maybe it requires a rare combination of chemistry and environment. Maybe microbial life is common and complex life is rare. Maybe even simple life is rare. The habitable zone cannot tell us which universe we live in, it only tells us where to act. There is also a problem with stability. A planet can be habitable in bursts. It may have temporary lakes, episodic melting, short warm periods. That may matter for chemistry. It may even matter for life in some scenarios. But a temporary puddle is not an ocean world. A brief thaw is not a stable biosphere. A possible warm interval is not a living surface. Headlines are poor at time. They make a world sound like it exists in one state. Planets are processed. A planet can move between dead and more promising states. It can lose air. It can gain air. It can freeze. It can thaw. It can outgas. It can be resurfaced. It can be sterilized near the surface while remaining active below. It can enter and exit windows of possibility long before any telescope exists to observe it. The habitable zone is a still image. Habitability is a film. That is why the best way to tell this story is not as a lecture, but as a stripping away. Take the perfect planet, give it the right orbit. Now ask what happens if the star is young and violent. The surface glows under repeated flares. Radiation breaks apart molecules high in the atmosphere. The upper air heats and expands. Hydrogen begins to escape. Water becomes vulnerable. Over millions of years, the ocean inventory shrinks. Oxygen may remain or react away. The planet still receives the right average light, but the star has already taken the water. Give the planet tidal locking. One side heats under permanent noon, the other freezes under permanent night. Winds scream from one hemisphere to the other if the atmosphere is thick enough. If it is too thin, heat transport fails. Volatiles may migrate to the night side and freeze. The terminator becomes the imagined refuge. A ring of twilight where temperatures might allow liquid water. But even that refuge depends on pressure, circulation, clouds, and chemistry. Give the planet too much carbon dioxide, the atmosphere thickens. Infrared radiation is trapped. The surface warms. Water vapor rises. Greenhouse feedback strengthens. The blue world becomes white cloud, then steam, then heat. The habitable zone did not prevent the greenhouse from becoming a trap. Give the planet too little atmosphere. The air thins. Pressure falls, water cannot persist, the ground. Temperature swings grow violent, any lake becomes temporary, any river becomes memory, any ocean becomes impossible at the surface. Give the planet no geology, carbon cycling weakens, climate regulation fails, volcanic replenishment fades, weathering cannot balance out gassing, the atmosphere drifts. The world falls toward heat or cold without the deep planetary engine that once could have pulled it back. Give the planet the wrong size, it cannot keep air, or it keeps too much. It becomes a dry rock or a mini Neptune. It falls between categories, too large for Earth, too small for Neptune, and not clearly a place with a solid surface under a friendly sky. Give the planet water, but too much, no continents, a global ocean hundreds of kilometers deep. High-pressure ice at depth may separate water from rock. Nutrient cycles may differ. Carbon cycling may behave unlike Earth's. It might still be interesting. It might even be habitable in some sense, but it is not the easy blue Earth people imagine. Give the planet clouds. Clouds can save or doom a world. On a slow-rotating or tidally locked planet near the inner edge, thick dayside clouds might reflect enough starlight to prevent overheating. In another climate, clouds might trap heat, hide the surface, or block observations. From far away, clouds may flatten spectra and make the atmosphere harder to read. They can be a climate actor and an observational mask. Every layer you peel back reveals another condition. This is why not enough is the honest phrase. The habitable zone is not enough. Size is not enough. Water is not enough. Atmosphere is not enough. A single molecule is not enough. Similarity to Earth in one way is not enough. A living world is not one correct answer. It is many correct answers surviving together. The strange thing is that this does not make the search smaller. It makes it larger. If habitability were just distance, the search would be almost boring. Find the orbit, classify the planet, move on. But because habitability is complex, every planet becomes a story. Every system becomes a set of experiments. Every dead world teaches us what not to assume. Every ambiguous atmosphere teaches us how nature imitates life. Every red dwarf planet tests whether common stars can host stable environments. Every sub-Neptune challenges the boundary between surface and sky. Every TRAPPIST-1 observation rewrites our expectations about small planets around small stars. The disappointment becomes part of the map. A dead world in the habitable zone is not useless. It is a warning label for future worlds. It says the orbit was right, but something else failed. Find what failed, and you learn what living planets require. This is how the search matures. It begins with counting planets, then sorting planets, then measuring atmospheres, then rejecting false hopes, then building a more precise language for the worlds that remain. The mature version of the search will not ask whether a planet is habitable. If the answer switch, it will ask what kind of habitability is possible. Surface, subsurface, temporary, ancient, future, marginal, stable, detectable, hidden. It will ask whether the planet is habitable for Earth-like life, for microbial life, for chemistry that has not yet crossed into biology, or for nothing at all. The word may fracture into categories. That is not weakness, that is precision. The old green band was useful when the map was empty. As the map fills, the labels must become sharper. There may be planets outside the classic habitable zone with subsurface oceans warmed by tidal energy. There may be icy worlds where life, if it exists, never sees a star. There may be rogue planets with thick atmospheres and internal heat. There may be moons around giant planets where tidal flexing keeps water liquid. These possibilities do not make the circumstellar habitable zone irrelevant. They remind us that life's possible habitats may not fit our most famous diagram. At the same time, the classic habitable zone remains central for one practical reason: atmospheric detection. A biosphere hidden under ice may be real and still nearly invisible from light years away. A surface biosphere under an atmosphere has a better chance of changing gases that telescopes can detect. That makes habitable zone rocky planets important not only because they may support life, but because they may reveal life. The search is shaped by what life needs and by what telescopes can see. Those are not the same thing. That difference matters. The easiest life to detect may not be the most common life. The most common life may be hidden. The most promising targets may be selected by observational convenience as much as biological probability. Red dwarf planets are attractive partly because their signals are stronger, not because they are automatically better homes. Sun-like stars are familiar, but Earth-like planets around them are harder to observe with transit spectroscopy. Every target list is a compromise between science and technology. The habitable zone sits at the center of that compromise. It tells us where visible, surface-based life might be possible. It cannot tell us where all life is. The universe may be stranger than our strategy. That should make us careful with certainty. A planet like K218b can become a symbol before it becomes understood. A planet in TRAPPIST-1 can become an imagined ocean before its atmosphere is constrained. A future world may show oxygen and methane, and people may want the story to end there. But the hard work will be to ask what else could produce this. Could water loss create oxygen? Could geology produce methane? Could photochemistry explain a signal? Could clouds distort the measurement? Could the star itself contaminate the spectrum? The more important the claim, the more patient the answer must be. That patience is not anti-wonder, it is respect for the size of the discovery. Finding life beyond Earth would be too important to rush. A false alarm would not merely embarrass science, it would train the public to treat future signals as hype. It would make real discovery harder to recognize. The search for life needs trust, and trust is built from careful language. That is why Habitable Zone must remain what it is. A useful beginning, not a promise, not a home address, not a quiet confession from the universe that life is waiting there. The search for life is not a straight line from planet to organism. It is a long corridor of filters, rocky enough, warm enough, wet enough, air enough, stable enough, protected enough, chemically active enough, old enough, amodable enough. Each filter can remove a world that once looked promising. The habitable zone is only one door in that corridor. A planet can pass through it and die at the next. This is the cognitive reversal the public rarely gets. The phrase habitable zone sounds generous, as if the universe is offering a special region where life becomes likely. The more precise view is harsher. The zone is where failure becomes interesting. Outside it, many worlds fail too obviously for surface water. Inside it, they fail in ways that teach us more. They fail through atmosphere, through star, through time, through chemistry, through climate, through the fragile art of not becoming Venus or Mars. Earth is not the average habitable zone planet. Earth is the one example that passed all the filters we know about, and perhaps many we do not. That should change the way we hear every announcement. A new Earth-sized world in the habitable zone is not the discovery of a second Earth. It is the discovery of a question that has survived the easiest rejection. That is still powerful, it deserves attention. But the attention should be sharper, less gullible, more adult. The phrase "could support life" should not make us imagine forests. It should make us ask what must still be proven. It should make us think of atmospheric pressure, stellar radiation, volatile loss, rotation, cloud feedback, greenhouse limits, water history, and spectral ambiguity. It should make us feel the distance between a possible world and a living one. That distance is the real drama. A headline gives you a planet in one breath. Science takes years to decide what kind of planet it is. The galaxy is not empty of hope. It is crowded with conditions. That is harder to sell, but better to understand. Imagine a future telescope staring at a small rocky planet around a nearby star. It separates the faint planetary light from the glare. It gathers photons that have touched the planet's atmosphere. The spectrum rise and fall. Molecules are inferred. Water vapor, perhaps. Carbon dioxide. Maybe methane. Maybe clouds. Maybe uncertainty bars wide enough to keep every claim unsettled. The world will not speak clearly. It will resist. Every living planet may be hidden behind layers of ambiguity. Every dead planet may imitate parts of life. Every claim will have to survive not only excitement, but hostile alternative explanations. That is how it should be. The search for life should be hard. The answer should not be given away by a green ring. The habitable zone myth is comforting because it makes the universe seem almost organized for us. It suggests that life has a visible address, that we only need better telescopes to find the worlds already waiting in the correct band of light. The truth is more severe and more magnificent. The universe makes planets in enormous numbers, then exposes them to violence, loss, instability, chance, and time. Some may remain gentle, some may not. Some may become living, most may never cross that line. A planet can be perfectly placed and still be nothing but stone. The thought feels bleak only if the purpose of astronomy is to confirm our fantasies. If the purpose is to understand reality, it is beautiful, because now the search becomes a real story. Not a treasure map with a green X, a forensic investigation across the galaxy. What happened to this world? What did its star do to it? Did it keep its air? Did it keep its water? Did it cool too far? Did it heat too much? Did its atmosphere lie to us? Did chemistry almost wake up and then fail? Did life begin, vanish, hide, or never appear? Every planet in the habitable zone becomes a mystery with a body, a history, and missing evidence that is far more interesting than the myth. The myth gives us a habitable world by naming it. Science makes the world earn the name. There is a strange mercy in that. When a planet turns out to be less Earth-like than hoped, it does not mean the search has failed. It means the universe is teaching us how not to be fooled. It means the next target can be judged better. It means models improve, instruments improve, language improves. Public understanding improves if we let it. The dead worlds are instructors. Venus teaches atmosphere. Mars teaches loss. Red dwarf planets teach stellar violence and tidal physics. TRAPPIST-1 teaches uncertainty. K218b teaches the danger of mistaking intriguing chemistry for a verdict. Earth teaches that habitability is not one factor, but a long alliance of factors that could have broken many times and did not. The habitable zone still matters because without it we would have less structure in the search. It helps astronomers choose targets. It helps frame questions. It helps compare planets around different stars. It focuses attention on places where surface liquid water is at least physically plausible. But the phrase must be spoken with its missing words attached. Habitable zone for liquid water, under suitable atmospheric conditions, not proof of habitability, not proof of life. That is less elegant. It is also closer to the truth. The public may prefer the shorter phrase, science cannot afford to. The next time a headline announces an Earth-like planet in the habitable zone, the right response is not cynicism. It is not to roll your eyes and assume the planet is dead. It is not to mock the excitement. Excitement is earned. We are living in an age where other worlds are no longer guesses. That is extraordinary. The right response is to hold two thoughts at once. This planet may matter. This planet may be nothing like the image in your mind. That tension is where real wonder lives. A living world beyond Earth would not be less miraculous because many candidates fail. It would be more miraculous. It would mean one planet passed through the gauntlet. It kept air. It kept water. It endured its star. It balanced heat. It preserved chemistry. It gave life room to begin and time to change the world. The discovery would not be a planet in the habitable zone. It would be a planet that survived the habitable zone. That is the better phrase, because the zone does not save a planet. The planet must survive everything the zone leaves out. The search for life is still one of the most powerful ideas in science. It touches the oldest human question with the newest machines. It takes light from distant stars and asks whether matter has learned to breathe somewhere else. It turns tiny spectral features into arguments about oceans, atmospheres, and biology. It asks whether Earth is alone without pretending the answer will be easy. The myth makes the search smaller by making it sound simple. The truth makes it vast. A green ring around a star is not the end of loneliness. It is where loneliness begins to be tested. Somewhere out there, a planet may sit in the right orbit with the wrong fate. Its sky may have been stripped away before life could begin. Its oceans may have boiled into space. Its night side may hold frozen gases under eternal dark. Its day side may burn under a red star that never moves. Its atmosphere may be thick, toxic, and closed. Its spectrum may tempt us with a molecule that means nothing biological at all. And somewhere else, perhaps, a planet sits in a similar ring and did not die. It kept enough, not everything. No planet keeps everything. Enough air, enough water, enough stability, enough protection, enough chemical tension, enough time. That is the world the search is trying to find, not a world labeled habitable. A world that actually is. Until then, the phrase must stay sharp. The habitable zone is not a home, it is not a promise, it is not a biological verdict, it is the place where a planet begins its argument with death. Most may lose, one may not, and if we ever find that one, the greatest part of the discovery will not be that it sat at the right distance from its star, it will be that the right distance was only the beginning, and somehow, against all the ways a world can fail, it became alive.